The genesis of this project is this Fortune or Victor lathe. Here in the shop, we've recently been building new chip pans for it. The ones that came with the lathe originally were attached, and basically the only way you could clean them is from the rear. And with a backsplash on the lathe, which this one has, it makes that impossible to do. So we've made some new ones and just need to finish that up. Also been doing some maintenance on the lathe. And if you look at this lathe, here is the description of all the, well, I call them quick change gears, but they're not. They're pulleys on this one. You do change the pulleys. And here are all the combinations. It gives you the tooth for each wheel or each pulley. And it gives you the designation over here as to where they go for each combination. And so what we have is a setup here with high torque timing belts that run the lead screw, the carriage. And so what we need to do here is to make the gears that we do not have so that we can appropriately operate the lathe through all feed rates and all threads, both SAE and metric. So the task at hand here is to make pulleys, gears, and what we have here is what I cut out of a piece of inch thick by 4 inch wide 6061 aluminum. And we're going to make pulleys for 20, 25, 28, 30, 35, 43, 50, 52, 54, and 70 tooth pulleys or gears. You can see the waste to the right there of what was left over. Pretty minimal. And also you can see here on this piece that we had to build up some additional weld material around the edge to get enough width. It saves me from having to buy an additional piece of stock for the wider pulley, but that turned out seems to be just fine. Each one of these will get a 20 millimeter hole in the center, as well as a keyway, a 6 millimeter keyway. We'll start by boring the center hole with a 3/4 inch drill, and then we'll ream it with the reamer we have here. I've changed out that R8 collet and installed the 20 millimeter reamer. And we're now going to ream that hole and hopefully get a better finish than what that drill left. Looks much nicer. Nice clean finish. Had to slow it down there a little bit to get that. So we go through the remaining blanks and cut the holes. I brought you back to the bench here where I have laid out each blank as well as one of these steel pulleys, gears, whatever you want to call them, from the lathe. As you can see, I've bored all the holes, reamed them, and I've also stamped each piece with the tooth count so that we know which is which. Next, we'll set up on the mill so that we can, I may trim some of the corners off the rest of these pieces in the bandsaw just to get it pared down a little bit, easier work in the lathe. We'll have to make a mandrel in the lathe to fix the workpiece on, maybe something with a nut on the end to hold it in the lathe, and then we'll cut each one of these blanks to size, And then we'll move on over to the radius table on the mill, where we're going to cut each one of the teeth. And one thing we need to cover is how to operate that radius table, given each one of these has a different number of teeth, and how do we index, given 360 degrees on the radius table, to get the proper location of each of the teeth and the proper count. I've done the math on that on a spreadsheet, and we'll talk about that, about how I did that, and how we're going to approximate the appropriate angle, so to speak, on the radius table when we cut the gears. So in order to turn down these blanks, I made a mandrel here with a shoulder on it, so that we place those on that mandrel, then we'll bore and tap for a bolt to go in the end to fix it to the mandrel, and then we can go about turning to our finish OD. We'll start with putting a pilot hole in there so that we get our drill to go in straight, and then we'll drill and tap it for 8mm by 1.25mm. Go ahead and get that set up with the tap. Brought you back here with this set up to tap, using the tailstock as a way to line up the tap and make sure we're starting squarely. Again, I decided to make this an M10 instead of 8 because I have a flange bolt. I think it's going to work just fine for what we need to do here. This is certainly not the sharpest tap in the world. Perhaps it makes sense to bring you back when this is done. It's kind of boring. We have the bolt installed in clamping the first smallest pulley to the mandrel. As you can see, we need to cut this to be 30.69. So we've got some material to remove. Need to put a DRO on this machine that reads metric, so it's 31.2. 30.95. Getting close. 30.8. 30.68. Close enough. Let me put a chamfer on that side. Now we just have to do the same thing to the remaining parts. Well, I managed to get all of the parts cut initially. I have a 25 and I have, I believe it's a 52 already. I don't need those. I went ahead and cut them out just to have them. And we'll use those probably as the test part to set up our gear cutter. You see here is what I'm going to use on the mill to cut that. And I've also modified the initial part that we were using in the lathe to mount the gears, pulleys. We'll mount that. Now what we have to do is figure out strategy for mounting this on a radius table in the lathe so that we can then take the cutter and produce each one of the grooves. So the next thing is to set up the fixture this, I guess, for cutting it in the mill. In order to cut the gears, we need to think of a couple different things. One is how to center this in the radius table. And there's a journal here that's 30 millimeters. So what I did is cut a shoulder onto this mandrel that will allow us to center that piece. Then we can clamp it down using typical hardware, like so. Illustrates how that will be held on. One of the main considerations, sorry about that, is we need enough clearance for this cutter to move past the gear to cut a complete, make a complete cut through there without crashing into the clamp and fixture here. So I believe this will get it. Next we'll set this up in the mill, get it trammed in, and then we have to determine the correct tool height. Shouldn't be too much trouble to get set up so that we can come in here then and cut the gears, or I'm sorry, cut the teeth around that way. So let me get that set up and I'll bring you back. And so here's the setup on the mill. You'll see we have the radius table trued in to the y-axis of the mill. And you'll see the cutter is equal to the midpoint of the mandrel there. One thing I found is when we put the pulley on, we don't quite get a complete pass through the part without the mill intersecting the radius table. And so what I did is I set the automatic stop to avoid a crash when we bring the mill back. It stops automatically, but in order to address this problem, I machined a 6mm spacer that will allow us to get the full cut across all of the threads. And we'll just use the same nut. We probably have 10, 12 mils of thread engagement on that, so, and good fit to the mandrel. So I think we're going to be just fine there. And with that, we are ready to start making chips. Here we are set up with the 28 tooth gear. I've already attempted the 25 tooth, as you can see here, and turned out very nice. The only issue I had with the cutting this gear was the fixture. Apparently it didn't have it tight enough, and at one point it began to rattle a little bit, and I realized at that point that it was loose. So tightened it, everything turned out fine. All the math works. So one thing I did notice is I was cutting it in one pass, and you'll see here the finish is not quite as nice as when I adjusted the depth for a cleanup cut. Cutting uphill, of course, this cutter is running in reverse, counterclockwise. So we're cutting, the cutting forces are pushing into the radius table instead of across the side. So we're getting pretty good finish from that. I think as we work out into the wider pulleys, we're going to see some deflection. We may have to get a game plan together on how to address that depending on the results. But so far so good, and we'll start cutting the number 28 tooth gear here next. Here we are set up for the first pass. We're going to cut this with the auto feed. We're going to just in 1/10 of a mil for the finished cut. Now we repeat 28 more times. And this, each one of these are, I believe, 52 count, teeth count on these. And you have a couple set screws to keep the nut on tight. Take the nut off, and you can pull off each one of these gears. Yeah, 52. And so that also has a spline in here. So the drive is primarily based on the spline that's in this shaft. And so what we have to do is something similar for our 43 tooth pulley. And so we'll have to make some of these guides that help keep the belt aligned and keep it from wandering, and apply those to our aluminum gear or pulley. I've just bored the center hole for the middle pulley to just a hair over 50 millimeter to fit on the intermediate shaft. I have some soft aluminum wrapped around the part here to keep the jaws from biting into the part. Now I need to pull in here and create a shoulder on this that will hold the piece that helps the belt ride true. So next order of operations here is to cut that shoulder. First off, we're going to want to find the edge here, set the travel to 0. We're going to take a 39 thousandth, about a mil deep cut here. Set the depth. And it goes without saying that the lathe will be running in verse here. That's to depth. Well, keep in mind that it was moving backwards. And with that, the shoulder is cut. We've machined that part, and similar to what came with the lathe, we have 43 tooth gear, and we also have less room to work with. Now, I'm not too worried about the discs themselves because they will be sandwiched on the when installed, and also you'll see the nut is large enough to actually retain the side guide on it as well. If I could ever get this started. So that would help to force clamp it, keep it in place, even if it were to come off. Because we don't have a lot of room here to physically attach the material. So what I think we'll do is probably epoxy that on, and as well as similar to what's been done here where it's been stamped. And I think it makes sense to actually use steel for that guide or flange or whatever you want to call it as well. So the dissimilar metals is not ideal. We don't have a shaper in this shop, so we have to make do with the lathe to cut these keyways as we discussed before. The trick here is to make certain that you don't take too rich a cut. The tool should only take a small shave at each time because you don't want to put that much pressure on your gearbox. It's not made to do that from the hand crank wheel. It is from the lead screw and the drive screw or drive shaft. So we just take our time and work our way up. I brought you back here to the workbench with the finished pulleys. You'll notice that the 43 tooth gear that goes in the drive transfer from belt to belt, I finished that. I did epoxy these on, and I cut these out on the plasma table out of aluminum. Because of the belt width, these are, we're using 3/4 wide belts. I think that's right, maybe 15 millimeter. Anyway, so what we did is just riveted those on to hold them permanently. And the rivet I used is one of these guys, flathead, 1/8 inch shank, and just bored a hole and then countersunk the top of that head. And here's what it looks like when it's been pounded in there. So I think plenty of holding power. These flanges really don't have anywhere to go because they're sandwiched into the drive assembly there. The only thing I have in terms of some concern is this pulley doesn't have a lot of meat. I tried to distribute that across 2 teeth, but with that keyway, that's a pretty thin piece of material, depending on the load on the lathe. And I can imagine, there's a fair amount of stress on that part when you've got the carriage moving quickly, making big chips. I may yet build another of these out of steel since I have everything set up. It probably makes sense to do so. But otherwise, we now have a full set of gears, pulleys, and we can use that to produce any feed speed or metric or SAE threads, imperial threads. So it looks like this project's turned out pretty well. It took a long time to do all this. Clearly, if a person had a handy CNC program made up to do this, it would be a fraction of the time it took me. But the finish is good. Materials I think should suffice with the exception of perhaps that gear, and we'll take a look at that. So thanks for coming along for this project.